Hello, hello. How is it going? Let me know if you can hear me okay. That is not what's meant to be showing. There we go. Hopefully that updates okay. Perfect. Cool. So I put a poll out on Twitter asking what people want to see. It was pretty close between some Laravel stuff and some Rust stuff. But since I've already tried recording a video on some Rust stuff and it went wrong, I figured I'd live stream and sort of pick up from where that video left off. So in the last stream, if you didn't catch it, we started doing some tokenization for a little language that I'm hoping to finish called Lagoon. It's a C-style language, so curly braces and parentheses and stuff to call functions. But it draws a lot of inspiration from Rust, JavaScript, PHP. So we did some tokenization, turn in a string of text like this into some sort of meaningful value. In this case, it's an enum, which represents the tokens. We did some basic keywords like fn, let, true, false, if, else, while. We also did some tokens, so left paren, right paren, and some strings, some numbers, some other stuff as well. And we wrote some tests, which is great, because tests are useful. So I tried recording a video. Let me just toggle that. So I tried recording a video to build the parser, or to start building the parser at least, which went well initially, and then as I was editing and exporting the video, it went corrupted, which is never good. So I'm just going to quickly walk through some of the stuff I did. So the generate function, which I wrote in the last stream, returns a vector of tokens, or just like an array of tokens basically, and then we're passing that into this parse function, and all that parse function does is construct a new parser, and it passes through the tokens as an iterable object. So it's not passing the raw vec through, instead it's passing an iterator through, which means you can do stuff like call next and pop and push effectively from the iterator. The parser then loops through all of the tokens internally and will present a statement. So the next method returns an optional statement. If no statement's found, then it doesn't get pushed. And there is some error handling that needs to be done. And then you return the program back to the caller. So in this case, we're storing it inside of an AST variable. And for now, we're just dumping out that AST. So if we scroll down a little bit, we'll end up in the parser itself. So the parser stores the tokens. This is the iterable object. So this isn't an iterator that loops over tokens. And it also stores the current token as well as the next token. And this is more for like locality reasons. We don't have to keep on calling get at a certain index. We can always hold the next token in memory, because that's probably going to determine what we do in some cases. So then we've just got a constructor where we pass through that iterable. We set the current to the end of file and the peak to the end of file, and we also assign the tokens. And the reason we do this is because we're not saying these are optional. They're sort of required. So we set them to just an empty token, essentially, or a none token. And that's why up here in parser read, if we pass, we're calling read here twice. So the first read will fill in the peak token, and the second read will fill in the current token and also the next peak token. So let's scroll down a little bit more. The main function inside of here is next. And next is going to return a result or a parse error. And now we've only really got one error type at the minute, and that is unexpected token. But that will be fleshed out in the future. So we say we're going to optionally return a statement, meaning we don't always have to, but if we find a statement, we'll return it. We'll say if the current token isn't end of file, meaning we've reached the end of our token stream, we're going to return none. Otherwise, we'll return the value of parse statement wrapped in a sum and an OK. And this question mark here, if you're not familiar with Rust, so this returns a result, meaning it's either a statement or it's a parse error. And there are methods here to say, if it is an error or if it is OK. But what this question mark does is unwraps the value. So if it's OK, it will return the statement. If it's an error, then it will pass that error up through the chain. So here, this will trigger the error. It will cause the program to panic because we're not catching it anywhere else. And then the error gets output in the console. We also wrote a pretty decent test suite. So we'll get to that in a second though. We'll go back up here to parse statement. It's just going to be easier for me to type. Parse statement. So the only things we've actually got tokens for at the minute, we've got functions, we've got let declarations. So, let name equal Ryan or whatever your name is. And we've also got if statements. So this is where we handle parsing those. So if we just go into the parse function method, just as an example, or maybe parse let is going to be a bit easier to understand. So we come into here and we say, well, we know that we're inside of the parse let method, so we can just read parse the let token. We don't worry about the let token anymore. We know we've got it, so we can just skip over it. And then we try to grab an identifier. Hello, Renee. We try to grab an identifier. So if you've got something like let name equal Ryan, this is the identifier right here. So we grab that and we read past it. And we turn that into a string. So identifier is just a type alias. So type identifier equals string. And calling the into method is going to turn that into a string. And then we've got the initial here. So this is, again, let name equal Ryan. The initial value is a string in this instance. So we'll check to see if there's an equal sign. If there is, we skip over it and we try to find some sort of expression. In that example, it was a string. Otherwise, we set it to none and we return a statement. So statement of type let declaration, and we give it the name and we give it the initial value. So that's the very basic, probably the simplest parsing strategy there is. Parse FN is a little bit more complicated because we have blocks. So if you've got FN main, perhaps, this is going to cause an error. Let me do a multi-line comment. If you've got FN main, then you can have code in here. You can have multiple lines of code. You might have let name equal Ryan, let age equal 100. You've got multiple lines here. You've got multiple statements inside of the function. So that involves a bit more work. Again, though, we skip over the function token because we've already got it. We check to see if we need to parse an identifier. If we do, then we expect there to be one. Otherwise, we're just using a fixture string or like a placeholder because we're supporting closures, anonymous functions. And then we expect a left paren or like a left parentheses. And then we start building up the list of parameters for that function. So we start with an empty vector, and we'll say until we reach a closing bracket or a right parentheses, we will expect an identifier, and we'll just push that to that vec. And I'm using a parameter struct here instead of just a plain string, so that I can easily change things in the future. It's clear that this is a parameter and not just a string. Obviously, you can have multiple parameters as well. You don't just have one parameter. You might have 2 or 3. So you'll separate those with a comma. So we're saying if it is a comma, then we'll just skip over it. And then we're expecting the right paren, so the closing bracket for the parameter list. Parsing out a block. So this is saying expect there to be a curly brace, a left curly brace. And until we find a right curly brace, so a token like this, until we see one of those, try and parse a statement out. Skip over that right brace and return the block. And then after all of that, we return a statement of type function declaration with the name, the params, and the body. And similar things happening for parsif. So again, we're skipping over the if. We're taking the condition, so if 2 is greater than 3 or something similar, and then we're trying to parse out a block, which will happen if it's true. And then if there's an else token, we expect the else token to be there, and we kind of know it is because we're already saying if there is one, do this. And then we pass out another block, and then we return a statement of type if, and we give it the condition, the then block, and the otherwise block. And then we also have the parse expression function, which is a little bit more complicated because we have things like precedence and priorities. They come into play. So you can see we're passing in a precedence here, and we're matching the current token. So if you've got a string, then it's going to be a string expression. If it's a number, if it's a boolean, if it's an identifier, if it's a function keyword, so fn, then we're going to use it as a closure. And this is a bit cheeky because we're passing out a function statement and then using the return value. That's more of a sort of ease of development thing. And then we've got prefix as well. So if you do like not is open. So you're trying to see if is open is falsy, or you might do -2 times 3. In this case, it's going to be -2 on its own, then times the 3 instead of 2 times 3 and then with the minus. So we check to see if there is a minus token or a bang token or an exclamation mark. We read over that token and we create a prefix expression. And we're going to see all this come up later on when we do some evaluation as well. And then this is where the precedent comes into it. So we're going to say, as long as we're not at the end of the file, as long as we're not on an empty token, and the current precedent is less than the specified precedence, meaning whatever's passed into the function, as long as that is less than the precedence for the current token, we'll try to pass some expression. And a good example of this is if I go into math. So let sum equal 2 plus 3. That's simple. We've only got we've got one operator and 2 operands. But in a more advanced example like this, where we've got 2 plus 3 times 2 over 2, how should this be evaluated? What order should things be done in? And mathematically, it should be done as 2 over 2, which is 1, and then 3 times that, and then 2 plus that. So you can understand this a bit better with some brackets. So we've got brackets around this, so this will be evaluated on its own. And then we've got brackets around this. So this is evaluated, and then 2 plus the result of this. So that's what the precedence is for. And you can see that if I go to the precedence, so we start here at 0, effectively, and then up to 1, up to 2, up to 3, up to 4. And you can see for plus and minus, we use the sum precedence. For the asterisk and the slash, we use the product. And because the sum is less than the product, when we get to something like 2 plus 3 times 4, the plus has a lower precedence than the multiplication. So that means all of this is figured out first, this is parsed first, and then we use that with that. Hopefully that makes a little bit of sense. Let me just get rid of some of those changes. Cool, so we can see what some of these structures look like if we do a cargo run, and we'll do the math one first. So you can see for that precedence example, we've got a let declaration with the name precedence, and the initial value is an infix expression, meaning there's some value on the left, there's an operator in the middle, and there's some value on the right. And we've got 2 on the left, and we're adding that to another infix expression where we've got 3 on the left, and then multiply as the operator. And then on the right hand side, we've got another infix expression with 2 on the left divided by 2. So you can kind of see what's going to happen here. When we evaluate this, we're going to evaluate the left hand side and then the right hand side. And then when we evaluate the right hand side, that's also going to try and evaluate the right hand side. And we'll get the 2 over the 2. We'll get the 3 times the result of that. And then we'll get 2 plus the result of this. And some of the other test files that we've got fn.lag. So we've got a function declaration. If I actually open that file, you can see we've got a function called say hello with a name parameter, and we're calling that function here. So we've got a function declaration with a let declaration inside of it, and then we've got a call expression, which is here on line 5. And I can probably use like Rust here or something so that I get some syntax highlighting. Okay, cool. So in terms of plans for the rest of the stream, we've been going for 20 minutes already. There was a brief catch up. The video was about 45 minutes long, so that's not too bad. I think I want to start building the actual interpreter, meaning we're going to take that abstract syntax tree and we're going to start to loop over it and actually, start doing some calculations. So the best way to do that is to take this math.lag file and try to run that. So I'm going to start by creating a new module called interpreter, and we'll create the corresponding file for that. And what is our interpreter going to be? It's going to be a struct. So we'll have a struct interpreter, and we'll just do debug and clone just by default. We're going to store the AST, and we're going to store this as an iterable as well. So we're going to need a lifetime on this. And that iterable is going to store some statements. And we also need to import the iter as well. So our interpreter has a lifetime, and the lifetime is just going to help the compiler figure out the longevity of this struct, so how long it can hold the resources for. So we've got an iterable of statement, and we can probably start implementing our interpreter. So we're going to implement it for the lifetime I, and let's just create a new function that returns self. Still need to wrap my head around Rust lifetimes. Yeah, they're a bit confusing at first. I think that alongside the borrow checker is probably the two main things that put people off of learning Rust. I mean, you don't really need to understand them. You kind of need to say, well, I need a lifetime, so I'll add a lifetime. There's not really a need to understand them as such. So we can return self here, and we can pass in the AST. Perfect. Let's also create a function called interpret, and this is going to use, we'll actually just include everything here. This is going to receive the AST as a program, and a program is just a type alias for a vector of statements. We're going to create a new interpreter, so we can say interpreter new. We can do AST iter. So it's going to create an iterable from our vector. And then we're going to want some sort of method in here to say interpreter run. This is going to need to have a mutable reference to itself. We'll say interpreter dot run. Perfect. And for now, we're not going to do any error handling right now, but later on we can do that. So what does run need to do? Well, in essence, run is just going to loop over or take those iterable values, so the statements, and evaluate them. So the best way to do that is to use a while loop. So let's just do a while loop in here. So we'll say while let some statement equals self.ast.next. So while there is some statement inside of the AST, next is a mutable method. So it has a side effect. It removes the item that you're receiving from the next method. While there is some statement in our AST, we want to run that. So let's create another method here called run statement. And we're going to pass this statement in. Perfect. We can just say self run statement. And the issue here is that we're receiving a reference to the statement. So, I mean, we can deref it just by calling clone for now. There's undoubtedly a better way to do that, but clone will remove the reference and return a solid object. Cool. So inside of our run statement method, we just need to match against that statement. We need to figure out what type of statement it is. I'll add a catch-all in for now and just say to do. And we'll just do this. So in our main function, let's just do interpreter, interpret, AST. And this is getting angry with us. That is because we haven't unwrapped this. So we're returning a result here. Which means we have to unwrap to get the AST that's inside of it. Cool, so we can pass that into interpret, and let's just try running something. So let's do cargo run. We'll do examples, math. And you can see we've not implemented the let declaration yet, so it's panicking, it's throwing an error. Not yet implemented, and then we're dumping out the statement. So the let declaration. So let's probably the easiest way to go. If we think about this some more though, it's all well and good being able to loop over the statement, but we've not got anywhere to store our values. We've not got anywhere to define the variables or to store functions. So we need some sort of environment. So I'm going to create a property here called environment. And I'm also going to create a new file over here called environment. And we're going to have a struct called environment. And for now, we can just use values. And it's going to be a hash map. So values is a hash map of strings and values. Let's also declare this module in here. So back in our interpreter, we can use the create environment all. So this is going to be an environment. We need to derive the debug and clone as well. So we've got an environment, and we also need to know what a value is. So right now we've got a handful of different values. So we've got strings, we've got numbers, we've got bools or booleans, we've got closures, and technically functions, although functions are going to be constants. So we'll leave those out for now. We'll start with these ones. So let's create a public enum called value. And we'll just start with numbers for now, since that's all our math is going to rely on. We also need to make sure this is debuggable and clonable. And that makes everyone happy, I think. We also need to store the environment up here. And now there's a slight problem with doing it this way. So our environment itself can only really be used by the interpreter at any one time. So what we actually need to introduce some interior mutability. I know that's a complex word. It sounds a bit crazy, but it just means that our environment will be able to mutate our environment even when there are immutable references to the data. So if at one point we say get this data and then we need to mutate the data later on, we'll be able to do that using something called a ref cell. So how about we do that now? Up the top we can use standard RC and standard where is ref cell? Oh, it's in cell. So standard cell and then ref cell. We're also going to need ref and ref mut. So our environment is actually going to be an RC ref cell, like so. And then down here, we can do RC new ref cell new and environment new. And we actually need to define this environment method. So let's implement our environment. We'll do pub fn new return self, and values is just a hash map, like so. Perfect. So let's actually start doing some evaluation. Let's try and get a variable or a let declaration working. So we're going to match against a statement of type let declaration. We're going to have a name and an initial. This value actually needs to be optional, I think, because sometimes we'll have no initial value. So we can say if initial is none, like so. And now we need to borrow the environment. We need to get a mutable reference to our environment so that we can set the value inside of that hash map. So let's create another function called envmut. and this is going to return a mutable reference to an environment, and we can just say ref cell borrow mutable, and then a reference to the environment, like so. So now we can say get a mutable reference to our environment, and add a new method to our environment called set, and this will be a mutable reference to self, and then we'll have the name of the variable, which needs to implement into string, and we also need to pass through a value. And then self.values.insert name.into, and then value. What's the problem here? Oh yeah, we've not actually returned anything from here. Cool. So if initial is none, then we can get the mutable reference to our environment, and then we can call set name, and we'll say none. Otherwise, so this is handling the empty case where we just say let name without a value. Otherwise, we need to evaluate the value of initial. So we can say let initial equal initial.unwrap. So this is now an expression. We'll say let value equal self.run expression, and we'll pass through that initial, and self.env.mut set name as value. Now our run expression doesn't exist yet, so let's go down here and define it. So we've got run expression and a mutable reference to self, and we're going to return an optional value, which is fine because that's exactly what it expects. And we're also passing through the expression. And similar to our run statement, we just need to match against the expression. And if the expression is a number, we'll do sum. Otherwise, we'll do to do, and we'll dump out that expression like we did earlier. If the value is a number, then we can return a value number as well. And this is the only one we've got at the moment. So let's create a new file actually. Let's do, we can use variables here. So we'll say let age equal 100. And if we do a cargo run of examples variables, we can see we've got no errors. But if we just do, if we add a dump method here, so dump, we'll just do debug self.clone or self.values.clone. And inside of our interpret method at the end, we can just do interpreter, or perhaps at the end of the run method instead. We'll say, so run, at the end we'll say self.environment. Well, this is a good point. We can only get a mutable reference, but we probably want a non-mutable reference as well, or an immutable reference. So let's do an env method. It doesn't need to be mutable, and this will return a reference to environment. And just like we did before, but without the mut, we can just do borrow self.environment, like so. And down here we can do self.env.dump. And now if we run, we have a problem. semicolon. And if we dump, we can see our age variable has been stored and it has some value which corresponds to a number, which is perfect, really. This has got me thinking a little bit, though, whether we want to introduce a null type, whether it's worth it. I don't think it is. I mean, having some isn't really an issue because we can just unwrap. And any time you try to use a empty value, something that is none, it would just generate a runtime error anyway. So we'll leave it like this for now. So that's a very basic interpreter. You just kind of loop over the statements and run some expressions and modify some state. So let's try and get our math working. I'll say 10 minutes or so. Let's try and get all of these working. So we've got 2 plus 3, 2 times 3, 3 minus 2, 3 divided by 2, and then this more complex case here. So to do this in our interpreter, you can kind of see what happens. We've not implemented infix, so this will be our first step. Inside of run expression, we'll say expression infix, and we've got a left, an op, and a right, and we'll use a block here. Take a sip of my drink. So the first thing we want to do is evaluate the left and the right hand side. So we can let left equals self dot run expression left, and let right equals self dot run expression right. This is going to cause a couple of issues though, because if we look at our left here, it's actually a boxed value. It's a smart pointer, so we just need to dereference that. And we can match against our operator. As a matter of fact, we probably don't want to do that. We probably want to match against a tuple of these like this, because then in here we can say, well, if it's some number and the op is add and the right hand side is some number, then we'll do well, we can unwrap these here. We can do left plus the right, and we also need to cast these into their values. So I'm going to add some helper methods to our value enum. We'll do toNumber, which will return an F64 and take a reference to self, or just self. We can match self, and if it's a number, we'll just return n, and otherwise we'll just do unreachable. So here we can say toNumber, and we're expecting a value to be returned, so we'll wrap that in value number, like so. Value moved here after use. That is because, well, we can just clone these for now, right? And here we'll just do to do. Because we haven't implemented that. Yeah, perfect. Although we don't even need these toNumber methods, because these are going to be values. We're evaluating those. So we've actually got the left and the right values here. So we can just say L plus R. And we should be able to get rid of those clones as well. Perfect. So in theory, if we remove this and evaluate that, let's just do it up here. So we get our values inside of our environment. We've got a variable called sum, and it is holding some number with the value 5, which is exactly what we're expecting because we're adding those together. So let's undo these and try to get all of these to run. We can copy and paste that line. We can say if we're multiplying, then we do this. If we are dividing, then we'll do that. And if we're subtracting, then we can do that. So this, in theory, should handle all of our cases. And it looks like it does. So we've got division, I can't spell, division. We've got subtraction, which is 3 minus 2, and that is equal to 1. We've got the sum, which is equal to 5, which is 2 plus 3. We've got division, which is 1.5, and that is 3 over 2. We've got product, which is 6, which is 2 times 3. And then we've got the precedence test, which is 5. So we can double check this. We can say 2 over 2 is 1. 3 times 1 is 3. 2 plus 3 is 5. Perfect. So we've done some basic stuff there. What else can we do? Let's start doing some functions, perhaps. Let's do closures. So in our closure, we're going to have let say hello equal a closure. It's going to accept a name, and we will actually no, we won't do this. Let's do something simpler. Print.lag. Let's implement some native functions. So a native function is a function that comes out of the box with the language. Print is a good example. You know, you might have echo in PHP or console.log in JavaScript. They're all native. So let's implement print. If we have a look at the minute, we've not got support for an expression statement. So we'll start there. We'll say statement, expression, and the expression statement holds an expression. We just need to say self.run expression. And we need to do that in a block because we're not expecting a return. So this will evaluate the expression. Perfect. And then the expression itself is a call expression. So down here, we can add a new arm and call that call. And if we take a look at this, we've got an identifier, which is just a string, remember, and we've got a vector of expressions. So the identifier is going to be the name of the function that we want to call. This doesn't really make sense though, because what we really want to do is support any callable expression. It doesn't have to be a string. So let's make this a box expression. And in the parser where we create this here, the left hand side is going to be the expression, so we can wrap that in a box like so. And then our test suite is going to start failing because we need to update these to be identifiers. So expression identifier. And it also needs to be a box. So let's just copy and paste this a couple of times. That there, like that, I suppose. And the same goes for this one. Yep. We'll put the vec on a new line, indent all of this, like so. So our test suite should be parsing, and it is. Perfect. No, don't get rid of that. So print, that is fine. What have I done? What have I done? That is what I did. So we need to support call expressions. So double check that. So we're going to have the callable on the right and the arguments on the left. And the callable itself is going to be a value. So let callable equals self dot run expression of callable. And callable is a value, which is good, although it needs to be unwrapped. And argument is also going to be a vector of expressions. So we can say arguments dot into iter dot map, and we'll receive an argument. And collect those back up. Although we have a type error there, so into iter, a is an expression. We run the expression, we unwrap. We need to say that this is a vec of values. Yep, perfect. Okay. And now we can match the callable, which is a value as well. So we're going to need to introduce a new value type, and we'll call this native function. It's going to have an arity. No, it won't. It will have a callback, which is going to be a function that receives the interpreter. So we'll use create interpreter. We need to make it public. So pub. We'll use the interpreter. It's going to receive an interpreter, and it will also receive a vector of values and optionally return a value like this. And because we're using we're storing a closure here, debug isn't going to be specific enough, so we need to implement that ourselves. So we'll get debug, we'll get formatter and result. And we can do implement debug for value, fn format, that returns a result, and we can just match against ourselves, which is here. We're going to write to the formatter, and this is going to be to do for now. We'll get a reference to ourselves instead. We'll say if we're a value number n, we'll do n dot toString. Does that work? And if we are a native function, then we're going to have a callback. Let's also store a name here as a string. We've got a name and a callback. We can do format. We'll put name there. We don't need the callback. And that should work. Yeah, that should compile at least. Nope. Patterns number, yeah, of course. So back in our interpreter, we need to say if this value is a native function, then we're just going to run the callback and pass a mutable reference to self as well as the arguments. Otherwise, we can say to do and let result equal that, or just return this directly. That should be good enough. What is the problem here? Expected enum. Yep, there we go. So let's do this. Is having a go at us. Expected enum environment value. Oh, right, okay, because we can just return that directly and just pass in self, because self is already a mutable reference, so we can just pass that straight in. So native function, and we really just need some way of defining these native functions to begin with, because what's going to happen is we're going to run expression is going to return a value, and if we put that into our environment, variant is never constructed, not yet, no. We'll create a method here called get, which optionally returns, and we can just get name dot into. That is going to return a reference. Let's do get mut instead and return a mutable reference to that value. So we're expecting that. Expected enum that, but we found this instead. We'll just unwrap it. Oh, right, okay. I see what's going on here. So we'll just have to do this for now. We'll unwrap and clone. Change that to a get. There we go. So get was returning an option containing an option. So we have to unwrap that to get the option. I'm likely going to change this at some point in the future because this feels a bit nasty. So we need a way to keep track of globals as well. So globals are going to be things like functions. If you define a function, it will be defined globally, so you can use it anywhere. So let's do use standard collections hash map, and globals is going to be a hash map new. If we receive an expression identifier, then we can say if self dot globals dot contains key n. So if the globals has a key with the value of n, which will be our identifier as a string, we can do self.globals.get n again, and that's going to return a reference. So can we just do n? Otherwise, we'll do self.env.get, and we'll do n like so. We'll do a straight return off of that, and we'll do that. This is going to return. Do we want to clone like that? Yeah, perfect. So if our globals contains a key of n, we'll return that out of the globals. So finally, let's create a function called define global function. It'll be a name that implements into string, and also a callback, which we can probably extract from our environment. We can do something up here like pub type native function callback equals. Take this native function callback, plop that up there, and then something's gone wrong here. This can just be native function callback. This won't return anything. Did I do something wrong there? Yeah, I needed a comma, semicolon. And then here, we can just say self.globals.insert name.into, and then a value of type native function, where the name is name.into, and the callback is the callback. And name is being borrowed, so we'll say let name equal name.into. We'll do name.clone and name. And now up here we can say interpreter dot define global function print, and pass in a function. Let's create a folder for our standard library, and we'll do mod standard lib, and do a pub fn print that receives an interpreter. So we're going to have to use cray interpreter as well as the value, and it also receives a vector of values and returns an optional value. So this is going to be ignored for now. This is going to be args, and print is going to return none by default. And we're going to only accept one argument. So let's say let arg equal args dot get 0 dot unwrap. Again, this is very naive. We want some error handling in here at some point. And then we can just say print line. Let's actually call the function print line instead. So print line, and we can say arg to string. This method doesn't exist, but if we go back to our environment, similar to our toNumber, let's do a toString on self, and that will return a string. We'll match self if we have a value of type string, which we also haven't implemented. Value string s to string. If we have a value of type string, then we can just do s. If we have a value of type number, then we can do n.toString. Otherwise, we'll say to do. We also need to support this as let's do create standard lib println. We also need to support this as an expression type. So expression string s is a value string s. Something's going wrong in here. Arg is behind a shared reference. Correct. What do we want to do about that? Clone it. Feels a bit dirty, but it will work. So let's try running this. Option unwrap on a none value source environment rs. That is because I've called it println and not print. Awesome. There we go. So function calls are halfway there. Native function calls are halfway there. So we've got hello lagoon being printed out. And if we look at the source of print.lag, we've got println, and we're passing through that string explicitly. So yeah, we've got native functions. That's pretty cool. The reason I've done these first is because we don't have to worry about scopes and swapping out environments and stuff like that. So this is a pretty good start. And I've been streaming for an hour, so I'll probably call it a day with that. The repository for this will be open. I'll put the link in the description of this stream. So if you enjoyed, if you want to help out, if you want to contribute to the language and learn some Rust, that would be pretty cool. Please feel free. And thank you for watching. I will catch you in the next stream.